both from Bosch, India, Bengaluru. They will be delivering their talk on the topic EMC for safe, automated, electrified, and connected mobility. So I know Vinish. I think Vinish is here. I know Vinish during
Yeah, yeah.
his MTech studies itself. Hi, Vinish.
Hi, hi.
Nice to see you.
Yeah.
Okay. Okay. So I am going to introduce you and your colleague. Okay. And I'm
Yeah,
happy to see you here. Okay.
yeah.
Nice to meet you.
Yeah, it's
Okay.
the
So I know
same.
Vinish
Yeah,
very well during his MTech studies at Department of Electronics, you said itself. Now he's working as an EMC engineer at Bosch. I think he recently joined there. And he has an overall experience of 9 years and in automated EMI, EMC, and which includes 1.5 years in Value Chennai as a senior EMC design engineer, and 3 years in Aptiv, Germany, and 5 years in Delphi, Bangalore, as an advanced EMC design engineer and EMC COE of Delphi, India. And he has an experience in products handling experience such as clusters, infotainment, and BCM. So presently, he's working as an EMC engineer at Bosch, Bangalore. So Kanti Kumar Chikam has finished his MTech from IIT Roorkee in RF and microwave. Presently, he's a architect at Bosch, Bangalore. So he has more than 10 years of experience in automated EMI EMC, which includes 7+ years in EMI EMC simulation and EMC debugging, and 2+ years in EMI EMC development and validation, and 1+years in high-speed design and EMC simulations. So he has more than 4 years of experience in RF front-end design and development for military applications. So he has got areas of interest in EMC design, root cause analysis, EMC simulation, debugging, high-speed board designing, etc. So both of you are very good experts in this field. So I welcomes both of you for this section. Okay, so I hope listeners you can raise your questions in the chat box and we can discuss your queries at the end of the session. So maybe now I can hand over the session to Vinish and Kanti Kumar Chikam. Okay, carry on.
yeah. Thank you, Sujit. Okay. Yeah, and also I thank Deepthi ma'am and Supriya miss, all supporting staffs for giving this opportunity. Uh, yeah, so let me share my screen. So, yeah, I was 2009 2011 MTech pass out batch. So it is rather a wonderful experience to share this regarding the EMC. So let me know once the screen has come. Is it visible?
Now it is visible. Yeah.
Okay. So, yeah. Uh, Before going to the topic, so I think we are talking about the EMC. So let's. You might have already seen in the automotive world regarding the booming of the electrifications, the automations. So you might have seen a lot of electric vehicles on the road, a lot of automated vehicles that has like parking and lane assistance. All those features are right now most there are availability of these automations also in the car and automotive industries actually. So and also regarding the connected mobility. It's connected to the GPS. It's connected between to the vehicle communication are also there. So these are all the features that are booming up in the industry, and the most prime important the safety. So which is also very much important when it comes to the automotive world actually. So and now let us take we are deep diving into what is EMC. It's we are not really deep diving. We will be taking only the brim of the EMC world. It's very vast. So let us go to the EMC. What are happening in the EMC world in this safe, automated, electrified, connected mobility? So that is the topic that we will be discussing today. So before going to the topics, like what is EMC? It's electromagnetic compatibility. So that's when you design any product, rather it be domestic, it is aerospace or it's automotive, it has to interact with the external environment. It has to interact with the internal environment. So when you design, it has to, so there can be external interferences which has to be curtailed it. So there are interferences that could come from the external source, and that there are also interferences that could go out from your unit. So you have to look on to all these aspect. So the interference that happens, that is called EMI, and the design aspect you put into it are called EMC, the design aspect, for both stopping the interferences and also for what to say, for not to interfere with the other units that are working coexisting in the environment. So this is what the electromagnetic compatibility in a very basic level it meant actually. So yeah, so going to the next slide, you can see here, like when you for example in an automotive world, you have the unit where when it goes into the external this, and it can interfere. There are a lot of interferences factors, like you have, which you might have already seen, like radio transmitting towers. There could be also like radars, that military radars or the air domes. So all these emits the noises. And apart from this, if your unit are also like an EMC source, when it goes into thousands, when it goes into a street or it goes to highways, it becomes multiplied, because there could be n number of such ECUs in the vehicle. So in different vehicles, so altogether it can to also lead to the clustered interferences actually. So apart from that, there are also like static discharges that you could see. The static discharges, when you get your body get charged up and you get discharged into the unit. So that all these are taken in the aspect of the designing. How do we take care of this aspect of designing? We have testing. So you have specific testing chambers that are needed to needed to comply, or that's how the EMC compliance has been met. So you test these issues in a predefined labs, so so that you are within the limit, you know what are the emissions coming, you know what are the how much it can um, withstand the noises actually that's coming in. So that's basic what we talk about there when you go to the external world. So before I go into the deep onto the EMC, I would like to know from the audience, like, do you have experienced any of the EMC in your day-to-day life, or have you experienced anything regarding this? Maybe you can unmute and uh, so that let it be live, so that it will be more interesting. Or maybe like why do you feel the EMC is important, especially when it comes to automotive? So if there are any buddy, you can either chat, put a ping, or uh, you can unmute and speak yourself. I can wait a minute.
Yeah, Vinesh, we usually
Yeah,
experience EMC uh, uh, during when we receive a phone call and speak to
yeah.
someone. That's a natural one. And
Correct,
in
correct. Yeah,
automotive, yeah, that's we
yeah.
usually everyone should have experienced that.
Yes. Yeah. There's a one basic interferences that you
Yeah.
generally would have met actually. So you could hear the sound of like interferences from the mobile. So this is a
Mm.
kind of EMC. So to thank you Sujit for that. I think it's Sujit, right? It had replied.
Yes.
Yeah. Okay. Yeah. So I would like to explain regarding one of the EMC problem that I had met. It was in 1992. So what happened is that in an ambulance there was a patient that was taken. He was having a cardiac arrest, and he was taken. Hello, maybe somebody can mute. Uh, yeah. Okay. Yeah, so what happened is that this patient had a cardiac arrest, and he was being taken to the hospital, but he had to be given the defibrillator defibrillator. So what happened is that the technician was trying to communicate with the was trying to communicate with the hospital colleagues, and he used a radio transmitter. This radio transmitter had interfered whenever he turns on this radio transmitter, it shuts off the defibrillator. So as a result, what happened, there was it caused the death of the patient. So the EMC might be like as sometimes maybe a negligible factor sometimes, but sometimes it can also cause the death of the person. So that's how it uh, that's the importance of the EMC when it comes to the automotive world actually. So it can the safety features, it can even take the life of a person. So that's a prior, that's importance how we look onto it actually. So yeah, now let's talk about the complexity that we see in the external field actually. So as explained earlier, there are various factors that automotive vehicle, or when a vehicle is on the road, so it can get interfered from the military radars. It can get interfered from the transmitters, handy transmitters, or the handy cams, handy mobile transmitters, which my police or the some specific person uses it, which has a very huge power. Or it can also from the the symbol mobile devices also. There are also the interference that caused from the mobile devices. So there are a lot of various factors that can affect the normal functionalities. So or it can interfere with the normal functionalities of the ECUs. And apart from this, ECU itself could be a culprit, could become a culprit, like for a very sensitive units like GPS or the ABS airbag systems. It should not rather turn on these features when you have a very noisy ECU sitting closer to it. It should not just turn on the airbag. So it could rather lead to a death of the person. So or it should not, like ABS failures or something. So these things should not happen. This is where the EMC actually pitch on into the real life or in the automotive world. So there are cases where it happened, the accidents, a lot of failures, and that's the lessons learned from the industries, from the OEMs, from the tier one suppliers. They have the lessons now, uh, learned previous experiences on this. So the on the external fields as well as the internal fields. And right now, what I am explaining is the external field. Now it goes to the internal field. So in the internal field, you could see like more than this is a general. You can see in an car is no more an pure mechanical. It is tied to a lot of electronics. Even if you think of the very simple component battery, it's no more a simple battery. It has a battery management units. So that's how it has high speed buses, it has low speed buses, it has a electronic control units communicating each and every minute, single seconds or milliseconds, which like ABS looks for fraction of seconds. So these all should not get interfered. So a lot of issues are working together to achieve the when you are on the wheel, these all are working together to achieve the goal that passenger should be safety and it should reach the destination where it is. So when it comes to uh, this one, you see the routing in the harness. This is how the complexity you see. There are these routing itself is are so complex. It can itself can act as an antenna. So these are where it itself inside a car, inside a vehicle itself could cause an interference. So these are all the factors that we have to look onto when you look onto ECU, electronic control unit, that been designed inside a vehicle. So this is another aspect of the EMC that speaks about the vastness of the EMC that we are dealing with. For example, EMC doesn't just specify into a radio frequency or a microwave frequency. It starts from a very low frequency, like kilohertz or hertz, and it can range from gigahertz, like 6 gigahertz, 12 gigahertz. And due to the new due to the more and more usage of the spectral content, we are the customers, and we are also asked to do into the higher and higher bands actually. So that because the noise are being spreaded across the frequency spectrum, so we have to be within those, we have to be compatible. So that's why we have to deal with these all frequencies. So looking onto the power, you can see that the power we are which we have to withstand is like 2000 watts, whereas the power it has to sometimes some of GPS module that has to function maybe at the power of millionth of volt actually. So you can imagine the distance, imagine the scale as like a distance of a 1 meter flag that is compared with the distance of the moon. So that's the vastness we are dealing with in the ECU. So you have to withstand the huge power, and also you have to be operating with a very low power levels also. So these are some of the things where you have to deal with when you are going into the EMC world. So this is the new trend which you could see already in the wheels, like the HV and LV, the HV vehicle high volt. So you have the high voltage sections already in the in the previous vehicles. There is only a 12-volt battery system, but due to the EV electrification, you have for the more power, you have the higher voltages and the batteries into it actually. So you have a separate system, so HV system and LV system. So again you have the voltages that could range from uh, thousands of volt, or like it may be operating at 1000 volt, it may be operating 400 volt, and also the ECUs may be working at zero 0.8 or like 1 volt or so. It's very minor role. So that's again, these are the transients. All these switching transients could have the spectral contents or its footprints in the emission bands actually, or the bands of the its operating contents. So that's the vastness what we will be dealing with. Okay, so how we look onto how these EMC the limits are being derived, especially for the tier 1 supplier, or how the EMCs are EMC or the limits are being derived. So basically when the vehicle manufacturers are vehicle manufacturers release its products to a specific country, they have their own, sometimes there are international norms, sometimes there are norms that are specific to a nation that has to be adhered actually. So based on those, and also the experience from the OEM, they have their own experience, each OEMs, like the OEMs are like OEM, I mean like GM or like Tata, all these are OEMs actually. So they have their own experience from where this EMC are being or the limits or norms are being derived actually. Once this EMC norms are being derived, it scales down to the component level. They derives into the component level. So the from this specification, the component level specifications are derived from the component level specification. So we will be discussing with the customer. So based on which, along with the tier 1 suppliers like Bosch, we'll be discussing with the customer to say to discuss on these norms, whether they could be adhered, and what are the based on the discussion, we come into a norms that has to be adhered for from the tier 1 supplier level actually, from the tier 1 service. So here from this requirement we go into the requirement that has to be put into our design, especially in the PCB design, the schematic, the mechanical aspect, the shielding. All those things are taken care, or all these things get derived from this OEM or from the component level requirement actually. The once the component level requirement, like the tier 1 suppliers like Bosch also will roll out its requirement to the IC suppliers, so that there will be the requirement that has to be met by the IC suppliers that are being put into the ECUs. So Basically the trend, if you see, I think okay, that may be coming into the next slide. So the for example, the power level, for example, we have to meet here in the vehicle level, it's 100 volt per meter. You could see the ECU would have to meet like 200 volt per meter, and at the component level it will be much more higher, like 400 or 1000 volt per meter. So that's how the requirement goes on. It's these all get derived from the experiences, from the tier one suppliers, from the OEMs. All that's how these requirements are being derived actually. So why do we take care onto the EMC? Is especially so here you could see the graph. So this is the product development. So it's a product cycle. When you design a product, if you are taking care of the EMC, the requirement, the design, the simulation aspect, the pre-compliance aspect, everything, if you're doing if you're strategically doing it in the very early stage, you will end up in a easy life, or like a very you could see here, when we are not doing all these tests like pre-compliance tests, or the design stages or the simulation stages at the very early stage, you will end up in testing it, and you will have a lot of failures at the very late stage, where you will not have much options, and you will end up in spending more money, more effort, and you can also lead to the shifting of the timeline. Later on, this also could lead to the dissatisfaction from the customer actually. So that's why the design stages of the EMCR, in the early design cycle of the EMC are very important, from the ECU design aspect actually. Not only ECU, it also comes in the vehicle level, as well as in the IC level. So right now we are more talking about the ECU level actually. So yeah, that's what we talk about. It will be like a time bomb actually. At the last minute, it will be, you will have to put a lot of effort, lot of money. It will be a restless environment then. Yeah. So in the Bosch world, what we have is a majorly three streams actually, three trees. The one that is aspect that takes on the EMC simulation part, ones that look on to the EMC development part, and one that's EMC test and compliance part. So the EMC simulation part, in detail, Kranti will be explaining you regarding the simulation aspects and what we take care in our Bosch. So these are the just a brief headings, like what we have. Some of the simulation that looks on the concept driven simulations, like looking on the shielding effectiveness, how much shielding effectiveness you may get it. The some other, like the failure driven simulations, that when you have failure and you look onto the surface currents, or you look onto the where how much power level has been injected. So these are some of the simulations, which anyway Kranti will be taking care of these things. So it's just an overview what I just told about here. The second aspect is like the EMC development phase actually, which again is like you look onto the design aspect, you look onto the there are layout rules, there are schematic rules that we will be taking care, and also you assess the ICs. For example, you are taking a new IC, you assess that what is the footprint, EMC footprints of those ICs actually. So that's how you deal with some of them. Then you have the pre-compliance testing. You look onto the debugging, where is the noise coming or what is getting failed. So these are some of the strategies, or the trees, EMC development trees, so that in the Bosch we have actually. And the next part is the EMC testing and compliance part actually. So once you have this design, you have to test it actually. So you have a DV testing, pre-DV testing. So you have to check whether DV testing, design validation testing, that's what I meant. So you have to check whether your designs are okay. So that's what meant by pre-compliance testing. It's in the very early stage, like before it goes to design, you have the proto model. So you look onto the pre-compliance testings actually. So how is the emission coming from each IC, from which section it is coming, and how can we fix it. So these all three branches interact each other, they have the simulation, co-simulation, they interact with the designers, they interact with the test engineers, and simulation engineers together correlate to drive onto the root causes and how we can fix those or early fixing of these solutions actually. So um, in the testing part, there is also the wing that looks onto the full compliance testing, where the final product is being tested. And there is also like automations, like you look onto. So what do you mean by like automation? Is like you have to monitor some of the functionality when it is being, when you are injecting, whether it is working properly or not. So these are things automated. So when once you find there is, okay, there is an error, there is noise, that or there is a failure, it notes down automatically which frequency, what orientation, and all these things are and what which register, all these things get captured. This is where the test automation people comes into picture. And the quality as which looks after whether you are injecting, whether the equipment that are being used are proper or not, whether you are injecting proper amount of power, whether the transfer characteristics of the antennas or the antennas or the devices that are being used are proper or not. So these are where the wings of the or the branches of these EMC testing and compliances actually. So yeah, let me move on to the next slide. And this is the four quadrant. The quadrant of the EMC testing is like uh, when you have an equipment inside the vehicle, there are the input lines, there are output lines. Input lines like power lines that is getting connected to the equipment for its power use. There are output lines that goes out, like there are flex rays, there are communication buses, all those things, that ethernet buses. So there are a lot of, and there are maybe also drivers. So these all are the lines that communicate with the external world, or communicate with the through the harness into the other ECUs, or the main systems, or the power line systems, or the communication buses. So what happens is that when your equipment is a noisy equipment, these all it can be, as you know, the antenna, these all will be acting like a carrier. It will be a conducting medium. It will carry this noise to other equipment. So these equipment can cause failure. um, that's why you have the conducted emission being tested actually. So conducted emission is like you can have the emission that is going out from the input line or output line. So that's what the conducted emission. Similarly, the opposite is the conducted immunity or conducted susceptibility. When you have the power line, there can be other equipments that could cause the noise, like you have the sudden switching. There is a turning on and off the inductor motors or the wiper motors. Suddenly you turn on and off. So there are a lot of spikes that comes into the power line. So these all noises, since the power lines are being equally are shared between different ECUs, this all noise will get traveled through the equipment section. This is the reason why sometimes you might have seen, when you put a third party devices which is not complying into the complying for this, sometimes it get failed very early stage actually. So these are the reasons where you could see, especially the conducted immunity or conducted susceptibility. It's also not only the power lines, it also the communication buses, or the other driver lines could also be a carrier for the noise actually, or the can be a susceptible part, so it can enter through the to the equipment through those sections actually. So those all parts will be tested for these noises actually. The next one is a radiated emission and the radiated susceptibility. So it's so here for the conducted emission and the conducted immunity, you need a power line, or you need a medium, or you need a conducting line. Whereas for the radiated emission, I think most of them might know it may be radiated. It can be either coupled through capacitively, it can be coupled through inductively, or it can be direct field radiation. So the radiated emission and radiated susceptibility, so it can be near field and also it can be far field. So all these comes in the radiated emission. So radiated emission, radiated susceptibility. So emission is like you can get in, you should not interfere with others, so you have the emission limit. So that's why the radiated emission comes into picture. And radiated susceptibility, that you should not also get interfered from other, so you have the design aspect over there. So that's where this radiated susceptibility comes into the, so these all are being tested for the ECUs for in a various based on the standards, for based on the international standards or the standards that are being specified from the OEMs. So the one more part that occurs in the day-to-day life, and also very prime important, is the electrostatic discharge. So it's like it can also go through the pins, it can also go through other parts also. So there where there is some small gaps, or the discharges, the static discharges could enter into the product and damage the ECUs. So these are the major quadrants where the EMC testings are looked onto. Okay, so okay, so this is one part, why one another aspect that really shows how the, like, when you go from the component level to the system level to the vehicle level testing, the factor, so that why this levels get stringent is also derived from one of some of these things actually. So you see here in the component level, when the effort, the cost that goes into is like 10 to 15 lakh, whereas when you have to look onto norms for the when you have to adhere for the testings in the sun in the ECU, it goes to 20 to 30 lakhs. And when you go to vehicle level or system level, it goes to very higher, almost 5 times when you treat it with the, when compare it with the IC level. So similarly, the effort and the factor also scales up drastically when you go from a component level to system level to ECU level, because there are n number of factors. For example, in the vehicle, when you are going to test in the vehicle, you have emission, you have thousands of, you are like more than hundreds of ECUs working together. It will be very difficult to really root cause. So that's why there are limits that goes into ECU. It's a similar case when you have the ECU have number of ICs that are happening. So something that can be dealt within the IC, it will be much cheaper, it will be much easily, it will be cost effective, it will be time, there will be also less time involved in it. But when you have like many ICs within the ECU, you will have a nightmare some of the times actually. So, and when it goes to vehicle level, if there are many of them, such as, you will have a for sure there will be a nightmare of nightmare from the EMCs actually. So that's how the critical, when it goes from climbs from the component level to subsystem level to the system level, it goes on. So now this is another aspect. So these, some of these are, you could see, these are some of the test facilities that is available in the Bosch. Some are available in the Bosch Koramangala, and some are in the Europe or in the external outside the country actually. So here you could see, this is what which I was explaining about. So from the system level, when you go to subsystem level to the component level, you could see the test level, the requirement will be getting stringent and stringent. So it goes like 100 because there are many things that are involved while deriving from 100 volt per meter to the 200. And when you go to IC level, like 400 volt per meter, the one of the simple thing is, like, for example, in the vehicle you have the harness length actually. So whereas here during the testing for the DUT, you have just 1.5 meter actually, whereas here you have the 10 meter also. Even the low frequencies, you can it can easily couple, even with a low power, it can easily couple the energy and throw it to the ECUs. That's the reason why you have an increased power level when you go into, because it's a standardized length, maybe like 1.5 meter, or for different testing they have different length. So roughly I'm talking about, like, it's in meters, like it is like below 2 meters, yeah, most mostly. So what happens is that the energy level that could enter is less, so you have to actually, to mimic the similar case, you have to inject more power. It's a similar case when you go to IC level, because again the traces are it goes here, you can couple with the longer cable length, but here the trace length will be very small, so you have to inject huge power into it actually to so it has to withstand such a huge amount of power. So this is the reason why these are the some of the subsystem testings or component level, how it goes, how it get derived from system level to subsystem level to the component level actually. And these are the jigs that are being used for the testing. You could see the test setup in the test setup details anyway. For the component level, I will be detail explaining you in few minutes. So I think this you are most familiar. Maybe already this is there available in the Kuzat, which is a fully anechoic chamber. But the most of the testing that has been taken for the automotive world, we test in the semi-anechoic chamber. So here we have the ground or the complete. Yeah, sorry. Maybe somebody can mute. Uh, yeah, thank you. Yeah. So just I will go through quickly. I think most of them are familiar over here. The what is the anechoic chamber? So why we are testing in the anechoic chamber? So basically, from your DOT will be tested on this bench. This is the conductive bench. This actually mimics the chassis of the vehicle, and here this the vehicle. This mimics the earth actually. So earth. So it's like a conducting. So here the duty will be placed, and since for example you have to have the radiated emission, you have to check the emission noise from the duty. So you do not want the interferences that is coming external, like you have you have the FM bands or AM bands and the mobile transmitters that are mobile transmitter bands. So all these bands can interfere with the issue, and you will not be able to understand what is the emission that is coming. So that is the basic necessity why we test the radiated emission, conducted emission. Also radiated immunity are being tested basically because you are injecting huge power into the system, and it should not interfere with the other that is external to that, and also to the operating persons, that it should not get affected to the those persons. So that's why these all tests are being conducted in it, and ALSE chamber, absorbed line shielded enclosure. So what happens is that there are waveguides through which the optical lines or there will be interactions with the ECU. For the ECU will be placed over here, and you have the accessories loaded. I think I will explain these things anyway in this. So the optical communication will be taken through these waveguides, all those things, and you have the antennas, different antennas for different bands. So this is the basic overview. I think most of them might be knowing um, about this LSE chamber actually. So let me go into some of the testing, which this is we have the test setup in our Bosch Koramangala. So this is the radiated emission test setup. In the EMC testing, as we talked earlier, this is one of the quadrant which we look onto is the radiated emission. So here we have, this is the ALSE chamber which we will be testing. You have the biconical antenna which tests for a frequency range from 30 megahertz to 200 megahertz. So you have the duty placed over here, and the duty will be loaded, will be there for the loading purpose. You have the accessories. For example, it has to drive some inductive load or some resistive load. You will be all will be done by putting in load box, or you have this accessory, or if you want to communicate with the duty over here, you have this communication buses over here, which will be there will be optical communication take happening over here. And like for example, you have to have CAN communication. CAN is the controller area network, which is the main earlier it was one of the main communication bus that been used. So for example, you want to communicate with this ECU with you have to check the frames, so you have to check the whether it is operating in proper functionality, whether it is properly loaded. So you have to check all these features. What happens is that you have the accessories over here, that includes the communication bus. So the communication bus, it will be digitally converted. From digital it will convert to opto, and through the optical links, you could see here there are a few lines. The optical links, it will be taken outside the chamber, and through this optical, it will be optical box, it will reconvert it to digital back and communicate with the system that is that is placed outside. So there we will be monitoring or putting into the functionality function into the functional modes which we are requiring. So basically, when we are testing for the radiated emission, we will be trying to put the DUT into the maximum MSC mode actually, so that we are capturing the maximum emission. So here you can see the antenna. This is just a pictorial diagram, pictorial representation. So antenna will be placed along 1 meter apart from here. Is that is a basic um, basic setup. Maybe it also depends from the customer to customer. Also, it may vary, but generally it is 1 meter from the DUT. And through the RF cable, you get into the EMI receiver over here. So you will be looking on the spectral content. What are the noise being picked up? So similarly, the duties that are the communication buses, that will be it's all also will be taken outside, and you will be monitoring. There will be one more block actually. So there through the boxes, through the computer or through the laptops or the systems, you will be monitoring the functionality, or through the oscilloscopes you will be monitoring its functionality. So yeah. Mm, okay, so these are the antennas which I already spoken. The biconical antenna that is seen over here. So here we generally take two polarizations. So there are different types of tests. Like you test it different ways. Like also like you have vertical polarization, you have horizontal polarization. So here you can see this biconical antenna is being kept in the mid of the harness actually. So basically, because you need the antenna length at these low frequencies, this 30 to 200 megahertz, and low period is 200 to 1 gigahertz. So I have, for these two testings, generally the antenna will be kept in the mid of the harness because it needs the antenna length. Then for the higher frequencies, like above 1 gigahertz to 12 gigahertz or higher, you have the horn antenna that is being placed, but it will be all most of the time will be facing directly towards the ECU. So it will be placed, it will be 1 meter, but it will be not in the mid of the harness, it will be mid of the it will be directly facing the DUT. So that's a test setup. And you have the, for low frequency, you have the monopole antenna. So these are the basic setup for the EMC radiated emission test setup actually. So the radiated immunity test setup are almost similar. Oh, the only thing is that you will be injecting power and you will be monitoring the functionalities. Earlier in the you will be putting into the operating mode. Here you will be monitoring during the injection for each. For example, you are injecting 200. Suppose you are injecting some frequencies like 200 megahertz. So you check for the operating whether it is functionally there, if the bus frames are okay, if the drivers are okay. If the memory units are okay, so you check all these procedures, and it will get for each frequency. So once it is okay, then you step into next frequency, 200, 204, 202, or something like it may be logarithmic varying, or it may be linearly varying based on again with the customer requirement actually. So the main thing what you can see is that the log periodic antenna is little big, or it is designed to withstand such a huge power actually. So you will be injecting like 700 watts or 400 watts of RF power. So it has the earlier previous antenna which I had shown may not withstand these powers actually. So you have a bigger antennas, or the design that take care of this one actually. And again, it is a the distance will be 1 meter, and here you will be monitoring the duty. So you can see a lot of optical cables, there are a lot of communications happening over here. So these communicate, it speaks with there will be monitoring externally for loading as well as monitoring purpose. You will be connecting with your maybe like a laptop or something that you can interfaces. So you will be checking during the operation mode. So for these you have the communication buses actually. And these are the loading things you have over here in the test bench on the left side, and this is a DUT. DUT is the device under test, or the ECU, whatever that is under test actually. So this is the horn antenna that's for the higher frequencies, like above 800 megahertz and higher. You have the horn antenna that so you will be injecting the power. It's a similar setup. You can say this is another one setup where the ECU is over here. It's directly facing towards the ECU. So again, the direction of the ECUs, it's also based on the discussion with the customer and the orientation. The ECU can be kept in X, Y, Z positions. So these all get discussed during the initial discussion with the customer. So because it also depends on the placement, how it is been placed in the vehicle also. So these are all these factors that we look onto the during the radiated immunity testing. This is another one. This is one another branch that you might have seen. So one in the quadrant of testing, radiated emission, radiated immunity. This is again another quadrant, conducted immunity is a bulk current injection. So here this is the basically this is for also for a low frequencies, like from kilohertz 150 kilohertz to 400 megahertz. You inject the RF power. Since at this low frequency you need the harness length, you inject this inductively. This is inductive as an injection probe, so it couples through inductively to the harness, into the harness, and you will be again monitoring its functionality through, you can see here, load box or the accessory loading things. You may not be always looking through the communication buses. You may also monitor through, like sometimes you have the clusters. You can see the front panels. You have to see whether the LEDs, whether the odometers are working properly, whether the LEDs are blinking properly. So these are being monitored externally through some cameras. So while during the injection, there will be a camera inside the chamber which can withstand the huge power. So you will be monitoring this the functionality of your equipment during the testing. So this is how the bulk. So this is how the immunity testings are being taken care. Here this is the duty. There is again it is being done in a shielded room with absorbers like fairy tale, because you are injecting power. It should not go outside and interfere with the other unit, because there's huge power, and also it can affect the testing person who is under charge for the testing actually. So basically you have the, here there's a block diagram, just explains a little bit in detail. So yes, in the amplifier there may be two sections for high frequency and low frequency part. So automatically this is where the automation comes in. It automatically switches from the low amplifier to high amplifier, and also it also monitors whether this is where the automation brings. It monitors whether the unit is failing, or unit is it will capture based on which frequency and what is the failure, all those things actually. So and you have the injection probe. This is what I explained previously. This is the injection probe. You have the injection probe. You are injecting, suppose like 200 milliamps or 100 milliamps. You are injecting over here from the amplifier. It goes to directional coupler. Here you actually look for the VSWR also. So what is the reflection coming back, which is also monitored through the software, and you inject the RF power into it. Once you inject into you look for the how much power is getting injected. For example, you want 100 milliamps of RF power into the cable. You monitor through here, through the power meter, whether that much power is getting injected into the harness. So again, there are going into detail, there are a lot of tests. Again, some of the tests like open loop and closed loop, let's not go into detail. This is a very basic touch on to the BCA, so that you get an idea of what is being tested. Again, it's a similar test for the conducted immunity. So this is what which I also talked earlier, like the conductor power lines could go, power lines or the input output lines could go everywhere. This is this pulse 1, pulse 2, A5, all are something that related to specifically to power lines. For example, pulse 5 is like when there is a disconnection from the battery, and it goes into the alternator. So only the loading is from the alternator actually. So the what happens is that the pulse can go, it will not be anymore 12 volt direct DC 12 volt, it will be alternating, it will be not alternating, it will go like go for a like a short duration to 70 volt, and then it comes back to 12 volt again, it goes to, it's basically the charging, and due to the inductive nature of the inductive nature of the this inductive loads or the alternators actually. So similarly, there are different pulses being tested for the conduct the power lines, as well as it is also being tested in the communication lines actually. But yeah, like pulse 3A 3B is something similar signal that could arise from the wiper turn on and off. So small inductive loads turning on and off, you could see this it can shoot up level to 150 volt for a short duration second. So all these aspect has been taken care during your design. So these are some of the pulses that we injected. So here you does not necessarily need a absorber, but maybe it is done in the shielded environment actually, but not really, the absorbers are not really needed actually for the testing. So again, here's the immunity test. So whenever you have immunity testing, you will monitor the functionalities of the duts are working properly, whether there is a reset happening, whether there is a uh, communication frames are getting properly delivered. So all these are being checked during the testing. Yeah. So again, this is a conducted emission. So this is another quadrant that which I already explained, this conducted emission setup. So you can see over here in the conducted emission setup, the this is a power and battery line. It will be connected to the LISN. It's called line impedance stabilization network. So what it does is that, because you don't know what network or what is the impedance that you see from the power lines, so it can be any. So to standardize and to get a repeated results, you have this line impedance stabilization network, which is defined as per the test international standards or the customer norms. So generally they have the specific license defined. So you will be here you have the 50 ohm termination. So this will be actually, you will be checking the noise through this cable. It will be connected to the EMI receiver. So the noise from the power and battery lines will be checked over here through the noise. And you have the accessories for the loading. This is a setup. This is a zoomed image of the setup. So you have all the accessories. You can see there could be a lot of maybe it may be a resistive loads, it may be inductive loads. Inside there is a load box setup, and you have the communication buses. So you have the communication bus, LIN or CAN or flex race, or so you have all it will not be communicated directly electrically outside, because it all can carry the noise or it can carry into or outside. So it will be generally uh, basically it's conducted emission, so we do not to take any electrically wired things until and unless it is purely filtered. So that's why the optical cables are relayed for, especially when you have communication buses to be monitored. So this communication buses you convert here through everything to digital to optical, and when outside you convert back to optical to digital, and then you look onto the bus frames actually. So, and this is one of the things that also might be come across day to day life, or most of them might have seen this one. So the air discharges or the static discharge, when human body, when or when you walk through a carpet, your body can get charged to like 25 or higher volt, 20 30 kV volt also. So you when you touch the electronics equipments, or you when you go into the vehicle, when your body is charged and you go touch the knobs of the infotainment, you touch the airbags, maybe the discharges can go into these units and can damage the things actually. So it can be, or maybe there may be technicians who are handling it, they may be turning, they may be operating it, they may be removing the harness and they may be checking the connections. So that time also, if their body is charged, and it can go into the vehicle harnesses actually, into the ECUs. So these all things are being tested over here. To mimic this, so that's these are the conditions where or sometimes when you are manufacturing, you have the handling cases, you are taking the unit and putting into the vehicle. So again, the technician might have a charge inside, himself to got charged, and you discharge into the DUT. So these all things has to be tested so that it doesn't fails during the functional, or before it get into functional, or during the functional time should not get failed due to this electrostatic discharges actually. So here what we have specifically for the testing purpose, we have the ESD gun. It's called the ESD gun. You can see here, for there are different types of testing. So for like contact discharge, you have different knob. Here you have the round knob for the air discharge. So how you represent, you look onto the current waveform. So there is a current waveform that mimics the discharge cycles actually of the ESD. So this is actually particularly calibrated for the ESD guns, are particularly calibrated for this such type discharges actually, and these are being discharged during the testing. Uh, this specific static ESD testing doesn't need any shielded room or anechoic chamber, but it needs a humidity controlled chamber actually, because it's the static discharge pretty much depends on the humidity of the air actually. So that's why you could see it is not a shielded room you here, it is a humidity controlled room, and you have the current controlled, these are all calibrated. This is the current waveform, and these are all calibrated accordingly based on the ESD, based on the which mimics the ESD discharges actually. So yeah, the voltage discharges can go, as explained earlier, to 25 kV or 25 kV or higher sometimes. So 25 kV is some of the max customer requirements. So your product has to withstand such a power onto it actually. Yeah. So before handling into Kranti, let me know if let me know if there is any questions, or else we can head over to Kranti for explaining into the EMC simulation part. Uh, Please let me know if
Manish,
there
I
is
think
any.
Manish,
Yeah.
we have
Yeah.
some queries on the chat box.
Okay.
Maybe I can read it for you, or
Okay. Whenever we discuss EV challenges, no one addresses much on EMI EMC issues. Is it because it is not relevant or not a challenge? No, no, no. It is a really a challenge actually. It's a real challenge. There are a lot of effort being taking put into this part. Maybe I cannot explain the design part much, but definitely you have the trans. For example, you have to there are DC-DC converters that there from 400 volt or thousands of volt, you convert back to 12 volt system. You have switching, you have a lot of load current. So these all transients actually cause a lot of noises. And also again as I told, there are battery management systems actually. So these all are again the ECU. There are a lot of ECU, they are communicating with each other. So these are all real challenges, and it's not sometimes also this especially this EV generally go into the low frequencies actually. So it's not necessarily you are having problems with the high frequency. You have the very low frequency, which is very difficult also to, sometimes very difficult to curtail. You need a big shielding, so you need a big you have to, there are a lot of aspects has to be taken care in this case actually. Yeah, yeah. So yeah, I think I addressed that point. Is it clear?
yeah, yeah.
Yeah, yeah.
So,
So will there be a difference in directivities of antenna used in both tests? I hope highly directional antenna is needed for immunity testing, as power should fall only on EUT. Okay, so directivity. So there are standard defined antennas actually. So there are different. Okay. See, for the low frequencies more than because basically it is a near field testing like 30 megahertz to 200 megahertz or 800 megahertz. You are testing within the 1 meter range actually. So it's basically a near field testing. So I think it's in the near field regime we are working. So the directivity more than directivity, it's that's the reason I talked about these testings are done basically in the mid of the harness because you need the antenna length to capture that frequency actually. So more the again for the high frequency like above 1 gigahertz you have the horn antenna. Actually that's a very directional antenna. So the power is actually injected towards the DUT. That's why the horn antennas when you are injecting are placed directly towards the DUT. But there are some customers also that points towards harness because there are also the chance that the harness resonance is also coming into the picture actually. Okay, the resonances I think maybe Kranti will take care of those most of the things. But yes, it's not about the directivity always actually. We are using directional antennas like horn antennas, and it's basically because of the first of all you have to have standardized setup, you have to have a you have to get a repeatability more than and it should be across the unit, it should be similar actually. So
Vinesh,
yeah so
in
I
that, I
think
have some small query in that particular
okay.
question.
Hmm.
Actually, EUT, whether you consider while considering the radiation emission, whether
Okay.
you orient or whether you rotate or whether you change the direction of EUT and you analyze
Yes,
which
yes, yes.
direction whether power is getting, rather than putting it fixed it in one particular location, whether you
Yeah,
try
yeah.
to rotate it or how it is.
So you mean during the validation cycle or during the
Emission
compliance
testing.
testing, what you or
During
okay.
emission testing, yeah.
Okay, so in general, what was so based on our designing and based on our experiences, what we know which sections could possibly get into the like more emissive, because we know where which side is ECU and which edges or all those things we will be looking onto, and based on these data we will be explaining to the customer, and based on that you will have some maybe sometimes XYZ orientation or only X orientation or XYZ or XY. So it's that's how generally, because when you test for all the possibilities, I think it may take it may not be easily possible actually, because there could be a lot of possibility. But the way how you deal is that you look onto possible emissive positions which you get more emissive part, and that part will be looked onto it actually. That
Okay.
section, that orientation will be taken into the, or if there are 2 3 you suspect two orientation, yes, you'd look onto two orientation. Yeah.
And different polarization.
Yes, definitely polarization is there. So polarization is not um, is not what to say is always been tested. You can most
Okay.
of the times
Okay.
it's been tested actually. Yeah, yeah, in
Okay.
vertical and horizontal polarization.
Okay.
Yeah, yeah.
Next question
So
is here, how the test
how
setup
the
of
test
DUT in
setup of
vacuum is done.
duty in vacuum is done? I didn't understand vacuum. We don't test in vacuum. It's automotive environment. So
Okay.
yeah, it's not in
Is it?
vacuum. Yeah.
Okay. Next question again.
Is it required to do EMI, EMC for battery? Okay, this uh, it's bit tricky question actually. So okay, so the battery, yes, in the I mean. Um, in the test labs, when you actually there are emissions also, there are susceptible emissions due to the chemical reaction that had come, that's little bit in the test lab, because it also increases the noise floor. But in general, as a like an electronic unit, you won't be testing it. But there are also sometimes the battery qualities are important when you are going for a testing actually. So because there are also some of lessons learned, like there are emissions that could happen from the design aspect that has been taken care in the battery part actually. But yes, not into the not like ECU level. That's what I understand actually. Yeah. kindly explain in detail about the impedance stabilization network actually. Okay. So you mean the line impedance stabilization network? I think it's they are talking about the line impedance.
Line impedance estimation network.
Okay, so the line impedance stabilization network, actually what happens is that internally, if you look, so it's from the standards, you internally, if you look, there is like there's a inductor. I forgot the value. There is an inductor, there is it's a LC circuit, and you have this getting matched into the 50 ohm load actually. So what happens is that the unknown impedance, actually the harness which are in the unknown impedance will be matched to this 50 ohm, because you should have a reference for measurement purpose. So that's how the line impedance stabilization network being done actually. So the internal part maybe I cannot show right now, but yeah, it's basically LC circuit actually, and it is been characterized for the 50 ohm impedance actually. Yeah.
Then always we are taking that characteristic impedance as a 50 ohm only.
Correct. It will be actually you are testing for like 30 megahertz, for example. In the conducted emission, you test from 150 kilohertz to the 108 megahertz or 200 megahertz. So you have to have this calibrated for those frequencies actually. So it has to have that characterization.
Thank you.
Yeah. Is there research work going on in Bosch to mitigate EMI in the design? Yes. There are design both, and so there are we have component level also design aspect looking onto. There are also in the simulation field, which anyway Kranti will be explaining. There are also like design aspect which looking onto the automation part, looking onto the AI part. So all these are there are where you can put artificial intelligence for example, you want to find out the particular filter characteristics, or you want to find some of the components that are being that are like could be competitive noise. All these things are being done. The research work is being done in the Bosch, Koramangala, as well as in the outside. Yeah, yeah. So in CISPR standard for RE measurements greater than 1 gigahertz will be positioned to DUT. Is it because the harness won't be contributing any emission at those frequencies, no matter what its configuration is? Okay, so here when it comes to the higher frequency, definitely the casing part is again those part again the Kranti will be explaining all these things actually also. So the casing parts will be the will definitely is the could also be the main emitters actually, because it comes into the antenna length actually. The 1 gigahertz, above 1 gigahertz you get like 30 centimeter. So even the casing part can be a direct radiation from those parts. So once the emission is there in the casing, it can be definitely coupled into the harness. So no matter you are it doesn't really need that antenna length of the harness. It can be direct emission from the DUT or the casing itself. So that is the reason why you directly point out instead of pointing into the harness. But there are also customers that also looks onto the harness part actually. So I just shown only the basic setup, but there are also some customer requirements. Sometimes they will also point out to the harness. In reality, I think that is clear, right? Yeah. In reality, what percentage of design qualify the EMC test? It's really a tricky question. So that's part which I had shown earlier. So if you really put effort, if you have already the designs aspect that been taken care in the very early stage, in the very early stage, you will end up in less problem actually. Sorry, maybe somebody.
Yeah.
Yeah. Okay. So it depends actually. So I cannot put a percentage over here, but if you are, if you have already experience of what unit, what all are, what could be the possibilities, I think you will have much more easier life. Maybe you will be coming with 90 percentage or 95 percentage good result. But maybe if you are completely new specs, new DUT, new ECUs, which are almost all of the case, then you will have more works. If you are not done at the early stage, then you will end up in disaster at the last moment actually. Yeah. How to calculate the EMI impact IC with respect to the RF and DC bias? Any theoretical analysis reference for EMI? So okay, a component level we are not much into. So right now it is in the ECU part. As explained earlier, this also comes derived from the experiences, as well as from it's also, there are theoretical papers that are available. So for the basic thumb rule is something similar. You, for the, as explained, in the vehicle level you have the harness coming into the picture. So you need you, even the low frequencies, you need the harness length is already available. When it comes to the duty testing, it's 1.5 to 2 meter. So you don't have that much harness length. So the coupling will be also much lesser. Once you have into IC level, you have to inject more power. That is a simple thing. So to mimic the similar cases actually. So the calculation part, maybe there are papers already available. That's what I remember. But yeah, right now I don't have any thing. Yeah.
Maybe I can share if one review paper. If somebody
Okay.
is interested, they can just go through, and from the reference of that paper, you can find some interesting papers that we are looking. Okay,
Yeah,
maybe
yeah.
I
I
can
think
share
already it is there
maybe.
in the available net. Yes, yes.
Yeah,
Yeah.
it's
Thank you.
available. A lot
Yes,
of
yes.
things.
Yeah, yeah. Thank you.
So I think
Maybe we
that's
will
all in the chat
go into,
box. Maybe
yeah,
the
we will
same
go to
is
simulation part. Yeah.
okay.
Yeah, yeah.
So Kranti.
Kranti. Yeah.
Hello, am I audible to everyone?
Yes, yes, Kranti.
Yes.
Okay, okay. I'm sharing my video, so I'm also, I think, visible. Hi everyone, good evening. Thanks, Vinesh, for your presentation. So I think I will continue on this topic. So I will now little bit dwell on this EMC simulation vertical. So as Vinesh has already explained, in Bosch world, we have three verticals. One is EMC simulation, one is EMC design and development, the other vertical is testing. So I have predominantly worked in the simulation area for last 10 years, and most of the time I was working as a simulation engineer and also a little bit of a debugging engineer also whenever there was some EMC issues at the test setups. So today I'm going to talk a little bit on the simulation, what in our Bosch environment we do, and in particular, me and Vinesh are working for a group which is right now called Chassis Control System. So we are more into this braking units which Bosch developed. So you might have already heard about ESP, ABS, eye boosters, and all. And so these are the active safety systems which we are working into. And so EMC is a very critical topic here. It's not just that we have to meet some standards of OEMs and all, because we are talking about braking, as Vinesh has already highlighted in the very beginning, that it is a life and death scenario, and a person's life is involved in this kind of systems which have to brake. It's emergency braking and all that. So in true, we have to make sure that our ECUs work no matter what kind of stringent environment they have put into. So this is what the compatibility, EMC compatibility means also for us, right? So our ECU, for what it has been designed, has to work exactly in the same way, no matter what is our environment, how harsh is our environment. So for that, we need to do a lot of efforts, as Vinesh has already shown you the product life cycle and the design life cycle. And the most time you put the efforts in the design cycle, the less efforts you need to put at the end. So this is a very important topic that is taken very seriously in Bosch. That's why they have been the pioneers, at least I can say, because of my experience. that they have started this EMC simulation area. We had development and testing long back, but as we understood that, okay, at the very beginning itself, we need to have a very concrete designs, and we should also see and analyze how different designs really work without even having a real hardware. So this is where we started to use this EMC simulation as a vertical, and also started creating an environment where we can develop simulation models and do some EMC analysis. So yeah, can we go to next slide, Vinesh? Once? So yeah, again, we are showing here the same verticals which we talked about. One important thing we need to highlight on the right corner, you can see we are showing the flags of India and Germany here. Why this highlighted is just to know that the same three verticals what we have here in Bosch India, we also have in Germany for working into this. So we have a mirror group. So whatever activities they are also doing in Germany, we also do the same thing here also. So more or less all our ideas or simulation approaches or even the testing and all are in line with our German standards, and we try to meet them because all our products are finally going into mostly to worldwide customers and also German customers. So we try to meet their standards, Indian requirements, and also their processes. So that is one thing this slide shows. So this is about our verticals. So this is not just applicable for our chassis control unit, but there are different units in Bosch. Okay, each of them, and they are different for each of the product. There are also EMC departments, and EMC departments sometimes can have all the three verticals, or sometimes can have one or two verticals, or sometimes they can also go to a centralized consultancy area for EMC, because there is one group which is a centralized location for the experts who are working in the area of EMC. They also work in the research area, also do research in area research for EMC, and particularly developing new simulation approaches, creating new models for us to use in our simulation setups, and also sometimes validating some of the test methods also, or if there's find some discrepancies for some particular reasons for some particular setup, there we go to that corporate research where they try to solve and give us the root cause for anything for that kind of problem. So this is how the Bosch world looks for us. Like there is like exclusively a lot of EMC groups for each of the business units, and each of the business units who are working for EMC can also have all these verticals. Yeah. So this is because, as I told you, most of the products which we are working are active safety or even passive safety like airbags. So we are talking about human lives here. So it's very taken seriously, and Bosch gives quality as the utmost importance for all its products. So that's why we try to have a very elaborate and a very well structured verticals. Yeah. So we can go to the next slide, Vinesh. Okay, so now let us try to understand how do I do simulation for EMC. Yeah, so as we already see that EMC, we are talking about emissions or immunity of your DOT. So DOT is basically an electronic product, right? So if you just keep out the active parts, the most of the things you see are traces on the PCB, components, passive components and all. So basically there are currents flowing through them. Okay, there will be some kind of fields coming out from them. Okay, and they can be coupling, they can be radiating. So basically what you see is some kind of electromagnetic phenomena taking place, right? So there are some excitation places where the signals are sent from one transmitter and they might be received at some other place. So there are excitation sources and there are receiving sources or loads and all this. So basically what you're seeing is an electromagnetic system, right? So basically, if you just, as for now, for this moment, we are just leaving out the active components, but the rest of the circuitry is basically in an electromagnetic environment. So how can you solve, how can you identify the currents or fields in an electromagnetic system? It's simple, right? You have to solve Maxwell equations, right? So if you can solve the Maxwell equations for the given system under given excitation condition, and you can compute the fields or any parameter, okay, of your required interest over the entire region or in a specific region, and then we can identify what is exactly happening in this scenario. So for example, here in the left bottom corner, you can see we have created a simulation environment where we have an antenna, okay, which is now being excited at its input port, okay, or at its input. And once it gets excited, it radiates, and you can see this fields propagate. And you can see on the left, we have this table. Okay, this is what Vinish was showing you, the anechoic chamber with the table. On the table we are putting our ECU and all that. So this entire setup, what you see in the actual measurement, can also be simulated in actual world. So here we are using some 3D solvers. Okay, so again, as I told you, we have to solve Maxwell equations. We have to solve sometimes Maxwell's equations in a 3D domain or sometimes in 2D domain. So here on the left, we are using complete 3D domain. We are trying to replicate the same scenario you would see in a anechoic chamber when you're doing an RE test or RI test or immunity test, right? So we have to create the same environment. We have to create the models for antenna. We have to create the table. We have to create the harnesses, then also the DUT, everything in this particular setup, and then excite. For example, when we are talking about immunity, we are trying to excite. We are exciting the antenna so that the antenna can generate some fields, and it can be impinged on your DUT, and we can see the immunity of the DUT to this to external fields. So this kind of things need to be done. So for that, we need a 3D solution. So here, what I'm showing is a full 3D solution where we are trying to create the complete environment. Yeah. And for that, we use some 3D tools like CST. Again, here you can see on the bottom. So this is one area where we are trying to work with 3D models. On the top center, you can see we also have 2D PCB simulation. Again, this is again, we are solving the same Maxwell's equations, okay? But now for some simple cases, for example, when we have to analyze something on a PCB, right? The PCB, more or less, our whole routing takes place in XY plane or YZ plane, any in one plane. And all the connections to the next layers are through some bias. So here, normally the fields, the variation of the fields along Z direction, yeah, is not so much. And or we can approximate that variation using some model. So sometimes we don't have to solve the entire 3D geometry, but we can use a 2D geometry and also can identify certain important things. For example, when I'm doing a high-speed design, right, I need to find whether the trace is having a proper impedance for the transmission line or not. We can do some 2D simulations because it's just a trace on one layer, okay? Or if you want to see whether there is a proper there is some resonance happening on the trace when it is getting excited, or is there some reflection at the load and all on a simple PCB, then we can use some kind of tools we call 2D tools or 2.5D tools, because 0.5D is just that in the Z direction the variation is not so much, so we can approximate certain parameters like bias and all using some simplified approaches. Yeah. So, or we can also say that only we solve in 2D cross sections. Yeah. So that is also one kind of simulation we do. Okay. And also the third one, what I'm showing on the right, is some simple network simulation. So this is more or less, for example, you need to start to design some filter for some particular DC-DC converter or some motor for filtering its switching noise and all. So you will start out choosing certain, based on your filter characteristics, you'll choose some values for the parameters, right? Inductors, capacitors, and all that. And for example, you might have value something, but in reality, the actual models parameters can be different. So you need to get vendor models and all that. And then once you incorporate, then you have to do some simulation. So for that, we'll just use simple 1D we call this 1D simulation or circuit simulations for which we use spice solvers, like what you might also get normally for using in your during your studies and all, like LT spice. So in Bosch world, we use Sabre, okay, which is basically a tool coming from Synopsys, where we can do not only simple AC analysis for filters and all, we can also do transient analysis here. And one important thing for this is, as I told you, like when we are solving only Maxwell equations, we are missing out the characteristics of an active device. For example, how can I incorporate that kind of device into my simulation? So that cannot be done directly in our 3D tools. So we use a thing called co-simulation, where we bring certain 3D, we solve some part in the 3D, then bring it into the circuit tools, and where we have the actual models for the active devices like MOSFETs, even ICs or any other active components, diodes, example, all those things. And we can do actually a transient analysis together with a 3D geometry. So those kind of things can be done together. And for that reason, we also need these spice tools, because we cannot directly just work with simple Maxwell equations and keep the whole analysis to electromagnetism, because we also know that they are active devices and we need to also incorporate certain models for that, because they also have influences on what and also necessary for some in some cases. Without them, we cannot really solve any electromagnetic problem. Yeah. So yeah, so that is more or less about the overall tools or approaches we use for solving, for using simulation. Yeah. Yeah, we can go to next slide, finish. So again, here I'm just trying to again detail you the thing, what I was talking about. For example, on the corner, you can see this is the actual setup where you have the biconical antenna, right? And that is radiating. And there on our table is our DOT with the harness and all. So the same environment we are trying to create in the virtual setup, or we call in the simulation setup. So we should have the model of the antenna. Then you may not able to see properly on the table the DUT and all, but you can see some box. So in this box will lie our DUT, harness, and everything. So we have a strategy where we divide the simulation into different domains. Why, I will tell you later, because sometimes what happens is, like when you're solving a very big problem like this is an anechoic chamber, which is some 10 meter by 10 meter length or something like that, right? So, or at least some few meters by few meters length, 3 meters by 3 meters length. So those kind of things, if you start solving, okay, sometimes it becomes too computationally expensive. So we have a strategy for certain parts. We use one kind of solver, and for certain parts we use a different kind of solver. So maybe this I can detail in the coming slide, but you just remember that it's not easy for you to solve a complex problem like this, what I'm showing you, because as you know that the solvers have to do something called meshing, meaning they try to break down the entire environment into small cells and then apply Maxwell equations on this cell. So as your size becomes bigger, and when you're trying to reach into higher frequency, the meshing size will also reduce, because your mesh, the smallest size that you need to break down will depend directly on the lambda of your frequency. So you go to higher frequency, your lambda becomes smaller and you need to do a lot of meshing. So this mesh, at each of this mesh location, it will solve for Maxwell equations. So it has to create a very big matrix. And this matrix computation becomes very, hardware expensive, because we need to have a high-end systems with RAMs going into some gigabits. For example, some setup like this, we could only solve using some 512 GB RAM setup. Yeah, so those kind of, it becomes computationally expensive, and also we cannot do everything in one particular solver. So we also use some what we call divide and conquer approach, or we use for certain parts a different solver and try to merge the solutions coming from different solutions, yeah, from different solvers. So this maybe I can just when we are coming to some thing, I can talk about this. Yeah, yeah, maybe We can go to next slide, Vinish. Yeah, so let me now come again to modeling. Yeah, so as I told you, right, when we are doing some 3D simulations and all, we have to create different setup environments, right? For example, the first setup was where I was showing an antenna, right? Antenna with the table and all. But apart from that, there are other things also, like for example, here we also have the TEM cell, so which is showing just on there. So that kind of, so all these things have to be developed in-house sometimes, because we are not directly getting all these models from external vendor. But we also have to develop in-house. And as I told you, maybe all these models are not coming from one only from the one business in your unit, but also from a corporate research unit, which is already developing these models and sharing with it, because these are general setups, general components that are used in your test setups, like antennas, or TEM cells, or strip lines, or any other setup, or ESD gun models and all that. So all those things are already developed in-house. We have an extensive library for all this test setup models for the test setups, antennas, all that. So all this you can see on the. Okay, apart from that, some things like for each business unit also has to develop. For example, our braking unit is one kind of system. So it will have certain parts. For example, it will have a PCB, it will have a motor, then it will have some mechanical connection, housing and all that. So this, again, for that also, we need to create models, 3D models, so that we can do this analysis, for example, in a CE setup, in a RE setup with the antenna on that. So for that, we need to create some ECU model. So that is what you can see on the right corner at the end. So this is an ECU setup, right? So here you can see a PCB is attached to a motor, and also a lot of components that are there on the ECU. Those also need to be modeled. As I told you, we cannot directly incorporate an active model to solve this in a CST or any 3D tool directly. But passive components, at least we could now model them. And most of the passive components for certain analysis, we can use simple RLC model, because as you might be aware that any capacitor or inductor will have its own parasitics, which we call the ESR for, or ESL for a capacitor, right? So it's a series parasitic inductance or a series resistance that comes into picture, and which will degrade the performance of the capacitor at high frequencies, right? So that to take into account, we need to have some parasitic value also added. So we have simple RLC kind of models, which we can incorporate for all the components that are there on the PCB, and then we can also directly use it in the simulation, because again, here these are passive components. We still can work with the Maxwell equations without going into the semiconductor, or doing other kind of transient analysis with some terminal models for the active devices. So all those things have to be done. We have to do this. We have to check our models. And this library is not done in a day. Okay, I am working for 10 years in my business unit, and it took almost 5 to 7 years to just build libraries for us, because all those models what we develop in-house have to be validated. Because you know that simulation, we are using certain tools, they have some accuracy limits, and also it depends on expertise of you. How did you model? And if something is wrong in your model, whatever result that comes from simulation will be completely useless. Yeah. So that's why we do a lot of validation, meaning that we do some small tests on a wet network analyzer for this particular antennas and all that, and try to see whether simulation model results are matching the same way with the actual measurements or not. So for everything, as much as possible, we try to do the validation. That is at every model level, meaning like component level. Maybe in one slide you can also I will also show what kind of what when I'm talking about component level modeling means. But even all the antennas, fixtures, structures, all has to be validated, and then we start building the models, combine them together and do actual simulation. And then we also have to see whether whatever our simulation is predicting, okay, is really matching with what we see in the measurement. Yeah, so that is also a big problem there. Because not always, okay, our results can be accurate. Some frequencies, because when you develop a model, you might have missed some high frequency modeling of that. Okay, so you might have just taken okay, whatever vendor has given, but all of a sudden you see that it's not matching anymore at a higher frequency. Then what you will do, you have to go back again to your measurement setup. You'd have to do some measurement where you can somehow extract the model's high frequency behavior. Yeah, and then you have to reinsert again back in your simulation and then see again, is it matching or not. Yeah, so this is a constant improvement that we have done through years, slowly building the models one by one, then putting in actual measurement setups like what we are showing here, and then seeing whether it's really matching our results. Again, here one more thing. Again, as I told you, all the simulations, we cannot always take into account the realistic excitation sources. Yeah, for example, we cannot get an noise coming out from an IC, yeah, or some kind of switching noise or arcing noise of a motor. So sometimes we don't have a real excitation sources. So we cannot always do a quantitative analysis, meaning I cannot tell from simulation whether that emission will be some 100 volt per meter, sorry, some dB microvolts per meter or something like that. I cannot tell, right? So, but at least I can give some general trends. Okay, meaning telling that, okay, if there are two designs, which design will be better? So I can do some qualitative analysis for that. So those are the areas we really target. Okay, so not a quantitative measurements, not with the actual quantitative thing what you see in the measurement. Yeah, so measurement is always your reality. Simulation is how good you are trying to come close to that reality. So the modeling, every aspect, it's not just about we in EMC call this as coupling path, meaning you have a noise source somewhere and you have a sink somewhere, and the structure in between is the coupling path. The coupling part has to be accurately modeled. So that is what we are targeting. And as long as we can analyze certain things just without having the actual source model, meaning that without the actual excitation, if you can get some hints of this coupling path, maybe in some frequency there is a resonance in our coupling path which is giving a higher resonance. We try to see what component in our structure is really giving rise to that kind of resonance, and we try to optimize it. Yeah, so those kind of simulations is what we really do. So to do all those things, we need to put a complete setup like what you see in a CE or BCI, and do the coupling path analysis, then identify what exactly, which part, is it something on the PCB, or is it some mechanical part that is having some parasitic that is giving rise to this kind of problems and all that. So this is an extensive thing. This is a very big task, and we have been strongly doing it. It's not just one business unit. We have a centralized business unit. They're also developing product models and all. So those is complex. And one more thing I would also like to show on the right in the center, you also can see some concentric circles and all that, right? So this is modeling of harness. See, again, harness, when we're talking about harnesses, for example, in our DUTs and all, we have 1 meter, 2 meter harness. It's a very big length, and you cannot directly put that model of the harness directly in 3D, because you can see the harness is containing a lot of wires, okay? And these wires can be twisted, turned, and also there will be twisted pairs inside that harness bundle and all. So this is a complex structure. And if you try to put all those harness, DUT, everything into a 3D setup, you will not be able to solve the problem with the resource you have. So what we do, again, as I have shown in the very beginning, that we for some cases where the field variation in certain direction can be assumed to be fixed, or in a defined manner, we can use 2D approaches. So here we also use what we call transmission line solver, or the 2D solvers to get some per unit length behavior of the system, and then we extrapolate for the given length of your harness. So again, the harness is simulated in a different solver, and all these models from coming out from different solvers, or even from measurements, or even from vendor, are put together in one particular setup, and we then do the combined simulation, yeah, or we call co-simulation in some cases, yeah. So this is how the simulation activities are done, involving all the modeling at different levels, yeah. Yeah, we can go to next slide, Vinesh. Yeah, again, here the same example what I was trying to show here. We are talking about the horn antenna. I'm just trying to show you how the fields excited from the horn antenna, how your table is reflecting them or diffracting them into two different directions. So basically, this is how we can really create a real situation, what is happening in your measurement chamber. Yeah, yeah. I think we can go to next slide. Yeah. So yeah, one more thing, as I told you, right? The component modeling is also has to be done extensively. Yeah, it's not that you can just use simple RLC model everywhere and every time. Yeah. So of course, the vendors who will, for example, here we are talking about a simple capacitor. Okay, and the capacitor, you might also get some simple S parameter data from the vendor directly from the site, or if you ask them, they can share them. Yeah. But these models are some linear models working for certain frequency range. For example, maybe they are not done for all the frequency range you require to. So you need to then have to get a model that works for higher frequency. What do? You have no other choice but do the measurements. So we do also in-house measurements of these components and extract those models. And we also have to keep a library for all these models. This is about the linear behavior. But EMC is, when we are talking about immunity or ESD, right? It's not always a linear, even for simple passive components like capacitors or chokes or ferrites. It's not linear when we are injecting high voltages or high capacitance or high currents into that system. For example, the capacitor. For example, when a ESD capacitor, right, it's going to see under this 25 kV of ESD discharge, it can see voltages of more than 200 volts across that point. So that capacitor, what you have modeled to be some 10 nanofarad or 1 microfarad will not be any more 1 microfarad or 10 nanofarad, whereas it gets derated, meaning at higher voltages, it will go down. So for that also, we need to create a large signal. This is what we call large signal modeling for our components. That also we do through measurements. We extract the information, then create the models and generate a library for that. Yeah, using some in-house tools and software routines. So this is how it has to be so extensively, because this kind of modeling, if you don't do, you cannot really predict what will happen under a ESD phenomena or under BCI or immunity phenomenon, what will happen. For example, you might come across common mode chokes or ferrites that are used to provide a high impedance part for your BCI currents. But okay, you might get a model from a vendor that shows some response, but you don't know what will happen if 100 milliamps of current is flowing in through that, or some 200 milliamps of. So again, there also we need to do this nonlinear modeling or large signal modeling for that. So all those things have to be got. We have to create them, and once you create the library, you can incorporate all those things in your simulation approaches, and then really can predict what is at least as much as possible close to the measurements. Of course, still we are not there. Even if we get even if we can get a very close match of 10, even 2 to 3 dB, in certain cases we are very happy. Okay, but our strategy at Bosch is not always to match what you see in the measurements. Okay, it's understanding a root cause for a failure, or what parameter in our system can be optimized. So those are the areas. We don't always see that whether we are measuring. If we should get some trends, what we see in the measurement, and based on that, we should identify the real culprit or the design point which we need to work on, and that is what we try to optimize. Yeah, so that is our approach always. So till now, not in all setups we could get a very good correlation with the measurement, but we always try to see that if we can identify what exactly is creating a higher emission. Is it some resonance in a PCB trace, or it's some harness with along with some termination at the end is creating some resonance for that, or some parasitics of some mechanical part is resonating with some inductive connection or something like that. So all those are the aspects of that is what is our strategy always, yeah, to identify that. Yeah, so I think we can go to the next slide. I think maybe before going to this thing, one more aspect I would also touch upon. One of our basic problem is our ASICs or ICs. Okay, so most of the time components and all we can do a lot of in-house measurements, yeah, but for ICs and all we cannot, because we need to operate that ICs or ASICs or microcontrollers a specialized chip. Okay, so sometimes it will be difficult for us to get always all the models, and also even the IC vendors will not give you a models which will try to incorporate this high frequency behavior, right? So they might give you IBs models which you can use it for some high speed design signal integrity purposes, but you cannot use the same model for immunity. Yeah, for example, when you say that when I put the same IBs model, will it show me whether my IC will fail or not? Something like that cannot be approached. So again, there is some bottleneck. Lucky for us is that some of our ICs are in-house designed, so we can work with those IC teams to identify a little bit the circuitry, or they can also work do some simulations and give some models for certain parts of our IC. Yeah, and that we can also use. Sometimes we call this black box modeling, where they also do some kind of measurement based analysis and generate failure criteria for that model and then share it with us, of course. Yeah, and apart from that, as I think Vinish also has touched upon, we also do some in-house IC testing. Okay, we call them FEMCA testing. So what we do is all the microcontrollers and all for certain of our products, we use test boards. We do some IC level measurements. Okay, we also have immunity test at IC level. We also have emission test at the IC level. We can take certain data from that and use as an input for our simulation, whether to see it's kind of way of when we have this kind of test, RE test, how much of current will be finally getting injected at the pin of that sensitive IC pin, and whether this will cause a failure or not. This will try to check with the actual measurement how much is the failure test level for that pin, and then what is we are seeing in the simulation, and based on that we can also predict to certain extent. It's not 100%, but to certain extent in some cases we always can also get that kind of simulation. So IC modeling is again a big domain, and that we are also continuously working on that area. Sometimes we have, if you are lucky to get that IC from in-house, we can easily work because it's all Bosch-owned. There is no IP involved, so we can share across the groups. But when it comes to external vendors, it's always difficult to get models. And also vendors will not be doing all this modeling for us because it's a cost thing that for them. So again, this is all, it all depends on the volumes you purchase from them, how you have, let us say, have some agreements with them during the purchase process and all that. Yeah, so I think this is about the modeling aspect. I think I could not go into every detailed aspect of it, but I just wanted to give you a bird's eye view what's happening at Bosch and what kind of simulations we do at Bosch. Yeah. So this is now in the next few slides, I'll just give you one simple design philosophy we use using simulation. Okay, how to optimize, because this is what we also try to see, right? How we are trying to incorporate simulation approaches in the very beginning to try to solve or at least optimize the optimize the designs in the very beginning stage itself. Yeah. So this is what I'll try to show in the next few slides. I think Vinesh, we can go to the next slide. Yeah. So this is a simple functional circuitry. Okay, I think you can see there is an inductor, then there is a switch in parallel, then a series diode and a capacitor. Okay, so if you just do some transient simulation for this, you will see all the nice little curves with yeah, over the time and also frequency. Yeah, but I think we can move on. But once you incorporate all these models into the actual PCB, right? So the PCB, you cannot connect them with a very small trace. You have to connect with some finite element trace. Or sometimes the models will have some package parasitics, right? So those things also will come into picture. So all those things together will create a completely different behavior. What you had a smooth rise and fall times, all of a sudden with this PCB parasitics involved, or the package parasitics, or some mechanical parts that are connecting them, all those things can all of a sudden destroy your smooth behavior of your circuitry. Yeah, and they can cause some kind of overshoots or ringing in your system. Yeah, and this is what is actually will cause the emissions for your system, right? Because all these transients will create a noise on the power rails, and this power rails is what you do measure during your CE setups, or even directly in RE emissions. Also, you can see the power rail emissions. So all these things can create problems. So what you have to do is at the design stage itself, we need to incorporate the effects of your routing, PCB, and other structures which will come into the part of your model. Yeah. So how do we do this? Okay, how do you optimize this? So going now, once we have once from the 3D model we extracted certain parameters, we combine those 3D model parasitics in our circuit simulation, and then do the simulation. Once you do the simulation, you see this red curve with ringing and all that. Now we have to find okay, what parameter is causing that ringing? Yeah, and how I can optimize that. Yeah. Can we go to the next? Yeah, see, so now this is where what we try to see, okay, there is some parasitic capacitance coming in parallel to the switching circuitry, and there is some series inductance in the diode. Okay, let me tweak this thing, let me tweak that, and let me see whether my ringing is reduced or not. So this we do, okay, and we'll get to know, okay, by varying this parameter, we will be able to optimize this. So once we did in the circuit level, then we have to use again to see how we can incorporate whatever changes we have done, how in the changes for those parasitic capacitances or inductors in our simulation. So we go back to the 3D model. Yeah, I think we can go to the next slide. Yeah, so this is the next step where whatever things we have seen that are improved my behavior of the transient, I'll try to now incorporate. For example, here the pins were separated and they were giving some big loop inductances. Now, as soon as we have brought them together, the loop inductance has reduced, and then we are able to optimize it. So this kind of things we'll first see, okay, from the circuit simulation, because circuit simulation, we can do a lot of things easily, because in the CAD geometry, you cannot always change and again run a 3D simulation and all. So from a CAD geometry, we are actually generating some simplified RLC model, and that we are tuning, then identifying which parameter which was tuned, and then we incorporate the same changes into the CAD model. So this is one of the way we are trying to optimize our designs, not at the component level itself, but even at the PCB level routing or some component distancing, placement, and all that. Yeah. Yeah, I think we can go. Yeah. So this is one example where we can see there was some problem in the measurement where on the right, on the left, you can see there is an emission peak that was coming there. Okay, so first thing what we did is we tried to do the same thing in simulation, same setup in simulation. Then once we identified, we are getting the same resonance peak in the simulation also, then we try to find what is the root cause of it and then optimize it. Once we optimized we got a red curve. And then once we identified that, okay, this is the solution for this, we incorporated again into our design. And when we are measured in measurement, we again found that this really worked, and we got a pass result for this frequency. Yeah. So this is how we are trying to work. It means first thing is we have to see what is the problem. We have to model everything that is required for that particular setup or measurement. And then once we have to match with the trends of the measurement, then when we know, okay, we are good with the models, then we try to optimize them, find the root cause for that resonance, then identify which parameters can be changed or optimized to reduce that problem. And then we incorporate that change and do a remeasurement and see whether we are meeting the requirements or not. So this is general simulation and measurement, how we work as an integrated team and solve problems. Yeah. I think that's the thing from my side. Okay, hopefully I could explain whatever we do in Bosch, particularly in the simulation area. Yeah, at least some few thing as a bird view. Yeah.
Kranti, you have some questions in the chat box. You can go through that.
Yeah, sure. Okay, the first question is, other than CST, what other software tools which can be used for EMC simulation? Okay, for 3D tools, there are many available in the market. Like, for example, ANSYS HFSS tools are quite also have an equal level of what to say, I would say, can also be used, and they also have the same kind of structure as a CST. Like, they also are based on 3D tools. Of course, the algorithms, the the modeling or the meshing techniques and all can be slightly different, but more or less they are also, apart from CST, other tools. I don't have much extensive idea, but what I could see was one good tool apart from CST is HFSS, or also ANSYS. Again, see, CST is just not one tool, but it's a suite, meaning it has multiple. As I told you, you can sometimes you have a 2.5D solver, sometimes you have a 3D solver, sometimes you have a circuit solver. So it comes as a suite. In that itself, you have a 2D solver, a 3D solver, again 3D solvers for different kinds of meshing techniques or different situations for antennas or antennas placed on platforms and all that. So like that for like that in the real market, you have multiple tools. I think FICO is also there. Again, it depends on your choice, on what product you use, and your experience and your competency with that. Because we at Bosch are a German company. We are predominantly working with CST more than 15-20 years. I don't know exactly when it started and all that, but so we do that, and we are using, because over the Bosch world, we try to what we call is harmonize, meaning like if all groups are working with one tool, the sharing of models will be easy. This is what is our strategy. So that's why we use CST. So this is something about 3D tools. Apart from that, for circuit simulations, I think you can use any tool there, as long as you should be able to get the models in that particular SPICE modeling program, because I think Saber, we have some dot extension, dot Saber, or some SPICE it can take, and some SPICE models it cannot take. So the compatibility issues will be there. So in again, for circuit simulation, you can use any different vendor tools, but it all depends on how you can generate a model for that. Okay, I hope I answered that question.
Yeah, you can go to the next question.
Yeah, well, how much of correlation can be attained from measurement to simulation? Yeah, this, as I told you in my also, that we don't have a strategy that we have to meet one-to-one our simulation, because the last graph also you can see that we are not matching in the entire frequency range, but we were able to identify exactly exactly at that resonance behavior and it was matching with our simulation. That was good enough. That is our strategy. So we don't do 100%. It should match everywhere at all frequencies for all test levels. Yeah. So that is our strategy. And correlation is good for certain measurements only, not every measurement. All other measurements, we still go with qualitative analysis. Yeah. Hopefully I answered that question too also. How do you compare and compensate the simulated EMC pre-compliance test results to actual practical environment pre-compliance test result if there happened a remarkable difference between the two scenarios? It's a very tough question. Yeah, compare and compensate. Again, the thing is, always I told you, measurement is always the reality. Simulation is not. If your simulation is not getting the right result, there's something wrong with your simulation, right? So this is the first thing. Of course, first thing the test engineer also need to check is whether he's testing properly with all the right measurement tools and all or not. That is one thing. Once it's established, the measurement is 100%. And then we have to go with our simulation and see where exactly is the difference. Is it some frequency range we are not matching, or over the complete frequency we are not matching? So we'll try to see what can be the root cause of it. Maybe see, as I told you, right, our modeling is not 100% because we have a limitations. We don't have models for everything, right? So we had always that limitation. So we have to see maybe this particular aspect was not included, and that's why we are not able to meet the test result. Or so what we'll try to do is we'll try to see we can somehow create a measurement model, take a measurement model for that, and then again re-simulate it and see again if it matches or not. Yeah, I guess that is also answered. Then how co-simulation between PCB domain and the 3D occurs? Okay, I am not clear with this question, but co-simulation is what we normally say when we have to do some transient simulations, okay, which involve some active devices, and also some part of this active devices are connected in a PCB or some component, which is again in a 3D, right? So that 3D and this active modeling cannot be combined in one simulation. So we have to what we have to do is like this active model, we have to use a Saber circuit, okay, Saber tool, and then for 3D we have to use CST, and then somehow link them together. Yeah, either link them offline or online. Offline meaning like do a complete 3D simulation, extract some model of the 3D, then 3D model as simple as parameters or some other model, SPICE model, and then bring it into Saber and do a transient simulation. So this is kind of co-simulation, you can say. The other thing is, even in CST, we have what we call Design Studio. Okay, Design Studio is where you can put your all your components and other things like schema, active components and all that. You can do some kind of transient simulation, and this transient simulation is actually linked directly to the 3D, meaning that some components are in 3D. Those also get excited together in this transient simulation. So that is something what we call co-simulation. But PCB domain and 3D, I don't get a clear picture there, because PCB is, again, PCB is also a kind of 3D structure. If you say that it also has some variation that you can directly import into a actual 3D as a 3D model in your CST. Yeah.
Maybe I can just give some points over there. So I asked the question about the PCB domain and 3D. So usually we will have the layered structures for the PCB. So the simulation kind of different when we are going with the 3D usual classic modeler. So is there any, so what I understood from the explanation was the PCB will be simulated in any other CST domain and coming and importing it to 3D domain. Is that so? Or the PCB itself will be simulated in CST?
Yeah, PCB also can be directly simulated in CST, but your approach is also okay. See, if you want to do PCB separately, okay, then again, see, the PCB will have some interface, for example, with a harness, right? Some connector region. So let us say you have simulated completely PCB in a some PCB solver. So you have defined some ports at the connector, then you have some source inside your PCB. You solve that problem. For that problem, you can get a S parameter file, right? You can put this S parameter file in CST as some as a in the schematic as some termination, and then for the other parts, for the mechanical parts or the harness part, you can do a complete 3D simulation. So that is what you can also do. But or else you can also directly import even the complete PCB into your 3D, okay, and then do the full simulation along with the piece. But again, this is what I told, right? It becomes computationally cost, because when you have all the complex things together, then it will become difficult for your system to solve that problem. Yeah. So instead, if you can do it separately and then create it a separate model for it, and then you can just use as terminal load or terminal what to say terminal transfer function, like that kind of thing, that is also okay. Yeah.
Yeah. So can we import the near field currents of the PCB and simulate in the 3D?
Okay. So that if that is your idea of yeah, there is also an approach like that. Okay. For example, if you have it, but I am not sure whether you can do in CST PCB Studio. PCB Studio is what you use for solving some PCB kind of structures. In that, what you have to create is a kind of box. I think you might have all know about this Huygens principle, right? So something like that. Once you have some computed the E and H fields on the surface of this Huygens box, you can take this Huygens box and put it in some other 3D, and then you can do a 3D simulation. So that is also possible. Yeah.
Okay. So on the same note, I have another question. So
No
usually
problem.
when we are just modeling, we will be taking the critical nets. So I just need to know the suggestion, whether we will go for the critical nets only, or is it possible, or is it more preferable to include all the nets?
I would always go with critical nets, because see, you should not computationally burden your system, right? Just and again, your choice of the nets which you want to avoid will also depend on your expertise. Also, for example, of course, you always need a reference for any trace, so you import the ground nets. But in certain cases, the ground nets are also connected to the, say, supply nets, okay? And in some frequency ranges, your reference cannot be just your ground net, but also supply nets for those traces. So you have to be taking care of that, so that you incorporate the right net for that particular simulation, yeah? And sometimes even in your schematic, some of these nets can be connected to for some other nets, and those things can have some be influence on your results. So you have to just go back and see what are the possible path when I excite this particular trace, can it take as a return path or coupling path and all that, and then you have to choose very cautiously. And for that you need experience, and I cannot generalize in general to tell that what nets you have to choose. But if you're not at all sure, of course you have to do with a full all the nets included. But yeah, that's again computationally burdening yourself. Yeah.
Okay. Yeah. Thank you.
No problem. Okay.
Whether
I think. Yeah. Sorry.
Whether this spice models available from the vendors, whether it is useful directly in this case.
Yeah, of course. In most of the cases, so simple components like capacitors and all, right, we could almost see that 90% of the cases they do match. Of course, if they have only measured up to 3, of course, if you're talking about spice models, they might have generated based on some measurements or some internal modeling of it, right? So normally they can be valid to any frequency range if you're talking about spice model, but in some cases they also give this as parameter model, so they will only have some measurement to certain frequency. So that is also sometimes limitation. But as I also suggested, for some cases, right, the spice models are not good enough. For example, for non-linear modeling and large signal modeling. So for those cases, at least we need to have some measurement-based models. So it's always, it's everything, every aspect in your simulation, you have to verify, re-verify. That is what it is. That's why in Bosch, as I told now, for each model, we try to always, as much as possible, do an in-house measurement, because that is what gives us more confidence on whatever results we are trying to extract from simulation. Yeah.
Thank
you. Yeah, please.
In the chat box. You can
software to 2D simulation, to do free or commercial.
Before that, we have one more question, Kranti. If you change the parameters, did you get the standard components available from market? Something like capacitor, resistor, or so? If not, then what will be your next approach?
Yeah, of course. See, as I told now, if you don't get that thing, you have to do some compromise. Of course, because even in our simulations, we just don't arbitrarily tune the values. Say if you have 1 nanofarad, we don't tune to 1.1 nanofarad and say it's matching. We also see what is available for us to do, and based on that only that step size we take. And of course, if it is not matching, we still try to see. For example, you can also have some combinations, right? For example, if you put a 1 nanofarad capacitor in parallel with some 100 picofarad, then you get 1.1 farad. So some combinations of that also we can try to optimize it, right? So this is also a strategy. And maybe if you are completely exhausted with any other combination, then you have to see, is there any other parameter that in the PCB parasitic that I can improve directly in the routing or something, and that can help me to meet the result requirement. Yeah.
And we have final one question: software to do 2D simulation free and commercial. Yeah, I think this I cannot answer for the entire public because I don't know exactly how many available. Student versions are available for CST also, right? Yeah, so. yeah, of course. Because we have to purchase everything. So again, the commercial viability and licensing, costing, and all we'll try to see, and we can 2D. I think student versions, even CST is providing, even HFS, because a lot of people want the young generation to come into this domain, work it, and because this is also helpful for us who are in the industry, right? You're already trained and all. I think it should be available. Cost and all, I don't know, but I think student version should be available. I don't know how the licensing, is it free for the entire life or they give you for 6 months, 3 months? That will depend from tool to tool. Yeah. Okay, I think there is no more questions. So, yeah, there is no more questions. So I thank Vinicius and Kranti Kumar for this wonderful talk, and hope it was very, very useful for all the new learners of EMC and EMI. So thank you very much.
Thank you. Thank you.
Thank you all. Thank you from our
thank
side
you all.
also. Thank you.
Yeah.
Thank you, Vinish and Kranti, for accepting our request to be a resource person. And indeed, it was a very interesting one with a lot of practical examples. I hope all of the participants are inspired to do more work in this domain. Thank you once again to Sujit also, sparing your time and making this session interesting. Yeah. So I think, shall we switch on our videos and take a snapshot? Nihal, is it over?
1 second, sir.
Okay.
Sir, could you stop the screen sharing?
Okay. Kranti, I think you have to stop your screen sharing.
Yeah. Yeah, got the picture.
Thank you all. Please fill in your feedback forms, and thank you, Vinish and Kranti, once again. Hope we have more such interaction with you in future also, and all the best for your future. And thank you, Sujit. So we'll come back tomorrow. We'll share the session details with you. We have got a speaker from Samir Chennai tomorrow. So see you tomorrow. Thank you.
Yeah. Thank you.
Thank you. Bye.